Okay, so last week we introduced a couple of probability distributions. Mostly they were discrete probability distributions, but we also introduced one continuous probability distribution, which was the continuous uniform distribution. This week, I would like to focus on more continuous distributions. So that's what we're going to be talking about now and possibly Thursday or Wednesday as well. And I would like to start with what I think, or what many people think is the most important probability distribution, at least the most relevant to physical and natural processes. And that is known as the normal distribution. Now, whether or not you've taken a statistics course before, you have probably already seen the normal distribution. And you may have seen it being plotted. You may have seen people talking about it. You may have seen data based on it. If the name normal distribution doesn't ring a bell, then just like Renee said in the chat, you can think of the words bell curve. Let me wait for this to adjust a little bit better. Just like Renee said in the chat, you can think of the bell curve, right? So you may have heard the normal distribution being called the bell curve. Sometimes it is also called the Gaussian distribution. And we'll explain why in a second. But the name most modern statistics textbooks give it, it's the normal distribution. Now, there's a reason why it's called a normal distribution. So for starters, we want to consider an experiment that is replicated. You can think of any experiment, you can think of the outcomes, and you can think of replicating the experiment. And perhaps an experiment with one or more outcomes or one or more random variables as part of your outcome. If you define a random variable x, that's basically the average or the total outcome of the experiment, and then you repeat the experiment multiple times, you'll notice that your random variable x will tend towards a central limit, right? And you'll also notice that the distribution will be bell-shaped. So when I say that the distribution will be bell-shaped, it's going to look something like a bell. Okay, not exactly like that, but kind of like a typical bell shape where you have kind of like the most recurrent values at the center, and the most extreme values actually have lower probability distributions. By the way, this is a probability density function. So you may already be familiar with this is, yeah, a probability density function. And the question is, well, why does that happen? Because many natural processes actually follow this distribution. You can think of anything. You can think of anything from height. You know, the average height of a 25-year-old male in the United States, or just 25-year-old male in general. You can think of things that are more behaviorally based, such as results of a survey. So, for example, you can think of something like political opinions, political leanings. You can think of a more physical process, a more mechanical process as well, you know, such as temperature distribution. You can think of many different processes, and the reality is that most physical processes, if you repeat them multiple times, if you repeat an experiment that observes these processes multiple times, your values are going to start to tend towards an average point, which we call a central value. Now, this is so recurrent and so common in physical and natural processes that we call it the normal distribution because of how common it is. But we also informally call it a bell curve due to its shape. Now, I think the bell curve is the most common way of calling this distribution, especially in general popular culture. I think bell curve is a pretty accepted term. Statistics textbooks tend to avoid wanting to use the term bell curve just because there are other probability distributions that are shaped like bells, even though they may not be normal distributions. But I think for the purposes of this class, when we say bell curve, we will most likely be referring to the normal distribution. I'm going to try to call it normal distribution throughout the rest of the class, but bell curve is still appropriate. I want to talk a little bit about where this distribution comes from at first. I think that will be important just to get a brief history, right, of what it is we're studying. So this normal distribution was first approximated by a French mathematician known as, or called, Abraham de Moivre, and he devised his theory as the central limit theorem. So let me just write this down so we have a bit of notes here. So this was Abraham de Moivre, and he devised a theory called the central limit theorem. Now we are going to have more time later in the future, in a future lesson, to talk about the central limit theorem in detail. But for now, what you want to know about the central limit theorem is that it states that a repetition of experiments multiple times, or random experiments, the outcomes will eventually start to tend towards a central limit. In other words, if I repeat an experiment multiple times, my outcomes won't tend towards an extreme limit. Instead, they will turn towards a central limit. Okay, that's what we call the central limit theorem. We're going to do a bit of a stronger mathematical introduction to it in a future section. Now, de Moivre's work was actually lost for some time, and so over a couple of decades and centuries, decades, his work was actually not available. Therefore, this distribution was independently formulated by a German mathematician and physicist, which we've probably all heard about before. His name is Carl Friedrich Gauss. So he formulated this distribution, and because of that, it took its name, right? It received the name of the Gaussian distribution. When I took statistics years ago, that was the name we gave to this curve. Nowadays, in order to acknowledge Abraham de Moivre's contributions towards this normal distribution, we typically just call it normal distribution, right? To avoid naming one or the other, since they both were able to formulate it. However, they both did so independently. So that is the normal distribution. It's a really, really interesting, really fun type of distribution. And we're going to see some examples in future classes regarding when we see the normal distribution. Like I said, most physical processes actually follow this type of distribution. And the idea is, as you can see, that the values that are most recurrent are always going to be central values, whereas the extremes are always going to be in the minority. And just like I mentioned, this applies to pretty much anything, not just physical and mechanical, but also behavioral, biological, essentially any process, and statistical, obviously. Essentially any process you can think of, essentially will try to follow a normal distribution. Now that all sounds fun, and I know we can get into a lot of fun parts regarding this, this type of distribution. However, let's first begin with the math. We want to get the math out of the way, like I mentioned, with these distributions before we want to actually start to see them. Because once we understand all the math behind it, we'll be able to see all these different types of phenomena, and we'll be able to identify them a little bit faster and easier. So let's start first with the math. Just like any other distribution, whenever you are wanting to study or analyze a probability distribution, you want to know what is its probability, right? So what is the probability mass or density function? And then you also know what its measures are. You want to know what its measures are: mean, variance, standard deviation. So let's start with the probability density function. As you can see, this is a continuous random variable, and being a continuous random variable, instead of a probability mass function, it will have a probability density function. The equation that Gauss derived for this type of distribution is a probability density function equal to the following expression. So this is the probability density function of a normal distribution. Notice that the probability density function here, as you can see, is already a function of its measures, right? We have mean, we have variance, we have standard deviation. So we're going to have all three measures in the probability density function. This also means that in order to find or plot the probability density function of a normal distribution, we actually need to already know the mean, the variance, and of course the standard deviation. And how we figure out the mean, the variance, and the standard deviation will be from data analysis, from an analysis of our outcomes, our experiments. So whereas with other probability distributions, we typically start with the probability mass or density function and then use that to determine the measures. In this case, we will actually determine the measures from our data and then use those measures to be able to plot the probability density function. Now, because the probability density function depends on my measures, and because my measures are typically known, we tend to write a special notation. We tend to use a special notation for the normal distribution. And that special notation, which is sometimes used in the book, is function capital N. So when I say capital N and give you a mean and a variance, then we know that we're talking about a normal distribution with a mean of mu and a variance of sigma squared. For example, if I were to write down n, function n of 1 and 2, I'm saying I'm looking for a normal distribution with a mean of 1 and a variance of 2. And of course, the standard deviation would be just square root of 2. So that is how we identify, right, a normal distribution. We'll try to use this notation just to avoid having to write down this equation multiple times. Hopefully, you're already realizing from this equation that perhaps finding out probability values using it is not going to be as easy, but let's give it a try first. This example is from your text. It relates to current measurements. So measurements of a current. So let's suppose that we are measuring the current in a strip of wire. And let's say that our measurements, we realize that they seem to follow a normal distribution. In other words, our measurements are tending towards a central value, right? And then the more extreme values have less recurrence. After analyzing our data, we find that our central value, or our mean, is going to be about 10 milliamperes. And our variance is going to be about 4 milliamperes squared. Remember, variance would be squared. Now, I would like to know, right, what the probability is that my measurement exceeds 13 milliamperes. In other words, I am looking for the probability that my random variable x is greater than 13. Remember, with a continuous random variable, we normally don't find probabilities of specific values. Instead, we find probabilities of intervals. Therefore, I'm looking for the interval of 13 to, well, we can just say infinity. Now, based on what you know about probabilities, or specifically based on what you know about continuous probability distributions, how can I formulate, right, this probability? What would that look like? You may recall that in order to find probabilities for a continuous random variable, we are going to have to, use this equation, but we can't just throw the equation and plug in numbers, right? There is something else we need to do. So does anybody remember how to formulate, right, a probability for a continuous random variable, given the probability density function? Exactly, that is correct. Renee in the chat says integrate the PDF from 13 to infinity, and that's exactly right? We know that the probability consists of integrating the probability density function across the range that you are searching. Now, in this case, my range is, well, greater than 13. Therefore, my integral will have to be from 13 all the way to infinity, right? Because that's what we want, greater than 13. I could write down my equation here. I think that'd be relatively simple. I have 1 over square root of 2 pi. What would sigma be? What would my standard deviation be here? 2. That's absolutely right, right? We know that variance is 4, therefore my standard deviation is the square root of that, which would be 2. Then exponent of, let's see, we have x minus my mean, which is 10, and then 2 times my variance, which is 4. And we just integrate that with respect to x. I'm going to give you about 30 seconds to figure out how to integrate this function. You have a constant value here that can be taken out of the integral, but let's see if we can figure out how to integrate this. Looks like our math geniuses are taking a break today. Any ideas? Natural log, Bailey? Yeah, e to the u. Okay, so you're suggesting using a substitution. These are really good suggestions. I'm going to want to try to spoil your fun a little bit and say that you're actually not going to be able to solve this integral analytically. Notice that even though you try to do a u substitution, if you were to try the traditional route, you're still going to be missing an x value outside of the exponent. So in short, right, this integral really cannot be solved analytically. So if we can't really solve it analytically, is there any other way we can try to solve this problem? Remember, on the last class, we found 2 different ways of solving for a uniform probability distribution. One was with the equation, integrating, and the other method, Bailey is absolutely right, is to graph it. So we could try a graphical method, just like Bailey says, right? We can try graphing this probability distribution, because when we're graphing, all we're doing is we're plotting this equation. We're no longer integrating anything, we're just plotting the equation itself. I'm just going to do a really rough graph where this value is my mean. So this would be my 10 right here. But anyway, just graphing it, if this is my mean, which I'm going to say it's 10, right? And after graphing my probability distribution, I could try to figure out where 13 is, right? What's the value for 13? And of course, we know that for a continuous random variable, the probability is simply the area under the curve of the probability density function, right? So if we can find the area under this curve, this will be the probability that my random variable is greater than 13. Of course, this extends to infinity, but you'll notice that when you graph this bell curve, you're going to get, you're going to get to a point where your values are, even though they're not exactly 0, they're going to be very, very close to 0, both before and after your distribution. So if we can graph this and we can find the area under the curve, which there are a lot of graphical methods to find areas under curves, then we could find that probability. Now, thankfully, right, if we were to if we just want an exact number, we can find it. Thankfully, you don't actually have to go through the trouble of graphing, right, and calculating areas under curves, because this probability distribution is so common, right? It's so recurrent in physical phenomena that people have already graphed these for us. In other words, these areas under curves for specific values have already been found. Now we're going to talk a little bit about that later, but now let's try to continue focusing on a graphical approach. We know that if we want to solve a normal distribution, integrating won't really be helpful because we can't really integrate this analytically. Instead, we got to find a numerical method. And that numerical method could be, right, expressed as a graphical method where we just plot our function and then calculate the area underneath that plot. There are many ways of finding this graphically. There are different programs that you can, set an axis, set a scale, and then it allows you to calculate the area over a shaded region. You can also find numerical methods of calculating areas under curves. There's many different ways. There's many different methods you can use. But like I said, we're gonna figure out, or we're gonna find out in just a second, that we won't need to go through these methods ourselves because other people have already done these, right, for us. Now, there are several standard values for a normal distribution. And while I don't condone memorizing values just because, these values are typically used very recurrently, right? Very frequently. And because they are used very frequently, you'll find that we're going to be using these values multiple times. So first, let me graph this out so that you understand what values I'm talking about. And of course, so that we can see a little bit of what a normal distribution looks like or should look like, okay, in terms of its measures. So if I graph my little bell curve here, the bell curve has to be symmetrical. I know it doesn't look symmetrical because of my drawing skills. But if I were to graph my little bell curve here, this scale is, this is whatever scale, right? It's just 0 can be wherever. And this is my probability density function. My first question to you would be, what would this value be? And just conceptually speaking, not a number, but conceptually speaking, what does this represent? The value that's right at the center. It's the mean, that's correct. So this value is always going to be mu, it's always going to be the mean. So we know that much. And now what we can do is, since we already know the mean and the variance, we should know the standard deviation as well as the square root of the variance. So what I'm going to try to find are now values that relate the mean and standard deviation. So I'm going to graph my mean minus 1 standard deviation. So this value is going to be mu minus s minus sigma. So mean minus 1 standard deviation. And on the other hand, on the other side, I'm going to graph my mean plus 1 standard deviation. Now, you know the following, right? You know that this graph is symmetrical. And because of the symmetry of this graph, my mean minus 1 standard deviation should be at the same distance as my mean plus 1 standard deviation. And they should have the same probability as well, probability density as well. So if I were to graph and find the area of under this curve, and that curve is my mean minus 1 standard deviation to my mean plus my standard deviation, you'll find that regardless of what the mean and the standard deviation are, so for any mean and for any standard deviation, this value will always be 68.27% of the entire graph. So if I find the area under the curve, and I can say the probability, right? We know that area under the curve is probability. So if I can find the probability that my random variable lies between my mean minus 1 standard deviation and my mean plus 1 standard deviation, and that probability, regardless of what the mean and standard deviation are, is always going to be 68.3%, always. So regardless of what we're looking at, if our range corresponds to mean plus or minus a standard deviation, then you know this is the probability that we are looking for. Likewise, if I would like to move 2 standard deviations, right? So let's say I'm now looking for my mean minus 2 standard deviations. And of course, my mean plus 2 standard deviations. And I were to try to find the area under that curve, that area would be about 95.5%. So you can see already that at a standard deviation from our data, we already have about a 68% probability of a value within that range. At 2 standard deviations away from our mean, we're already looking at 95%, right? So that means that most of our values should probably be within 1 standard deviation of the mean. And that's really the definition, the conceptual definition of a standard deviation, right? We mentioned that standard deviation was a dispersion, right? And that dispersion can be seen here, right? The closer it is to the mean, the higher the probability. When you're already 2 standard deviations away, then you're already, right, considering or including most of your possible values. I could also try to find my mean, and let me get a different color. Let's try green, light green. I could also try to go at 3 standard deviations. And at 3 standard deviations, if I were to want to find the area under that curve, you can expect that it's going to be already very, very close to 1. It's going to be very, very close to 100%. In fact, the area under the curve, that's 3 standard deviations away from the mean, is about 99.7%. So what this tells us, and hopefully you are starting to realize this, is that if your physical process follows a normal distribution, which, as we know, most natural processes follow normal distributions, then you'll be able to confidently say that a large majority of your data lies within 3 standard deviations of your mean. So that means that that should help you, right, try to predict your values with a sense of accuracy. In that, values that are more than 3 standard deviations away from your mean are very, very, very unlikely to show up in your experiment repetitions. Recall back to the first week of class, or maybe the second week of class, when we defined probability. We said that from a more statistical point of view, probability was the limiting value when you repeat an experiment multiple times. And of course, we care about repeating experiments an infinite number of times. We say that if we repeat an experiment an infinite number of times, we should have an infinite number of outcomes. And those infinite number of outcomes are distributed along this bell curve. So even though, yes, there is a chance, however small it is, there is a chance of an extreme value, we can already recognize it as extreme value. We can already recognize it as an outlier or extreme in your data set. I don't want to get too far into the talk of outliers right now, because we will reserve those for when we talk about descriptive statistics. But what I do want you to realize is that our normal distribution is always going to follow these parameters. And you'll see that more than 99% of your data, almost 100% of your data, lies within 3 standard deviations of your mean. Now, we've talked about this, and I'm glad we more or less were able to see the probability density function and how it works. But we've also seen that finding these values requires some sort of graphical method. Now, here's the thing. You'll notice that your mean and your variance are going to shape, of course, your curve. So what we would like to do now is we'd like to find a value for our mean and variance that makes my curve a little bit easier to graph and just a little bit easier to understand. We know that regardless of mean and variance and standard deviation, all these values will remain the same. But we would still like to find a form of the bell curve, a form of the normal distribution that allows us to calculate things with ease. And that is what we call a standard normal distribution. We know normal because it is the most recurrent distribution in many natural processes. But now we're going to call it standard because we're going to use this as a standard for our normal distributions. So first, let's define a standard normal random variable. a standard normal random variable, which we typically define with a capital Z, is essentially a normal distribution or a normal random variable that has a mean of 0 and a variance of 1. So my Z is going to be a normal distribution with a mean of 0 and a variance of 1. If we were to plot this, we'll still get the same bell curve. However, we'll get a much more simplified bell curve. I mean, you can look at the PDF yourself to see what this would look like. For example, for a standard normal random variable, the probability density function, I can just write my probability density function for my normal random variable, which will be 1 over square root of 2 pi. Because the variance is 1, the standard deviation is 1. This will be multiplied by e to the power of, here my mean is 0, so x minus 0, just x squared. And that is divided by 2 times sigma squared, which is 1. So this would be my equation. So you can see from the get-go, it's a much simpler equation. You'll see that we'll have an easier time trying to graph this equation. It's going to be hard, still close to impossible to integrate it analytically, but at least the equation itself is a little bit simpler. Let me see if I can adjust. Looks a little bit better. At least the equation itself is a little bit simpler to use. The distribution of a standard normal random variable is typically denoted with the Greek letter capital phi. So we say that phi of some value z is equal to the probability that my standard normal random variable z is less than or equal to that value little z. So notice that phi is actually a cumulative distribution, right? It's the probability that my standard normal random variable z is less than or equal to my given variable z, my given value z. Graphically, what does that mean? I'm just going to plot this again. If we set a standard normal random variable where the mean is 0 and the variance is 1, which means that most of my data is going to be somewhere between -3 and 3, right? Between 3 standard deviations from the mean. Then what I can say, right, is that if I define some value little z, then phi of z is the probability that my random variable is less than or equal to this little z. So it'll be equal to the area under the curve before z. So this is phi of z, this area, which is the probability that z is less than or equal to little z. So that is my standard normal distribution. That's how I define my standard normal random variable. And you may be asking, well, what's the point of all this? I mean, it makes the equation a little bit simpler, but we still have to go into a graphical method. The reason we do this is because if we are able to express our other random variable, our other probability distributions in terms of this standard normal distribution, then we can use that to find areas under curves. And that's what many people have done. I mean, the values for z are so widely used that they are usually tabulated and can easily be found online or in the textbook. These tables are called z-values or z-score tables. So these values have been tabulated, and they're usually called z-value tables or z-score tables. And what happens is that for any given z, you are able to find the probability because it has been tabulated, which means that you don't really have to find it graphically. Now, it's important for you to understand what this means graphically, because you'll see that given the symmetry and what we know of the different measures of a normal distribution, then we should be able to find some relationships between probabilities. Regardless, these values have already been tabulated. Your textbook actually has a big table with z-score values. In your textbook, it is in Appendix 3. So if you go to our Appendix A, so if you go to Table 3 of Appendix A, you'll find what's called a cumulative standard normal distribution. And what this gives you is for different values of z, it gives you the probability, the area under the curve. And this is actually a big table that extends across 2 full pages. And it ranges from negative 3.9 to positive 3.9. You know that most of your data set will be included between negative 3 and 3. This goes a little bit further to give you even more distribution, more probabilities. I would like to talk a little bit about how we read this table, and we will do an example where we actually use this table and refer back to this table. So, but just to give you a bit of an idea, because pretty much every z-score table is the same, what you have here are the leading digits of your z value, and what you have here are the remaining digits of your z value. So for example, if I would like to find the probability that z is less than or equal to, let's say, negative 2.46, then what I have to do is find the leading values first, so negative 2.4. And to that, I have to add the remaining digits. So negative 2.4, but I'm looking for negative 2.46, which means that I have to add negative 0.06. So I find the remaining digit, and where these two intersect, that is my probability. We're going to do an example using this. Typically, z-score tables are divided between negative z-scores, which are values less than 0, and you can see that all these values are negative, and positive z-scores, which are values greater than 0, and you can see that all these values are positive. But the table still means the same thing. So negative and positive, and still read in the same way. This z-score table will be your best friend pretty much throughout the remainder of this class, because whenever we have to look at some sort of distribution, you are most likely going to have to find a tabulated value instead of calculating a value yourself. You may feel a little bit cheated now because I've forced you to calculate some values in previous classes, but you'll find that since most of our natural phenomena have normal distributions, then we will be able to use these tables to find these probabilities. Like I said, these tables are very common. You don't have to simply depend on the textbook. You can actually find them online relatively easily. And just to show you how easy it is to find them online, I actually just opened a search box and I just wrote z-score table. And I'll just show you some of the results that I got from that search. So this is just a standard search for a z-score table. And you can see, first of all, that it does recognize what it's talking about, standard normal table, which is my phi function. And you have several results, and pretty much all of these first results give you the z-score table that we're looking for, okay? And all those z-score tables are the same. You have here your negative z-scores, right? And you have here your positive z-scores, but they are all read in the same way. The textbook actually goes all the way through 3.9, so perhaps the textbook table may be a little bit more helpful. So it's very easy to find z-score tables online. You just have to search for a z-score table. I think the key here will be to understand how to read them, how to actually use them in order to find your probabilities. And let's get some practice on that. We could definitely try to practice how to use these tables. And I think we should try to practice how to use these tables, okay? This example, once again, comes from your textbook. Let's say, okay, that z is a standard normal random variable. I mean, that's how we typically try to define z, right, as a standard normal random variable. I would like to know what is the probability that z is less than or equal to 1.5. So first, I want you to try it. Let me know what results you get, and then we'll do it together. But I'd like to see some results. What is the probability that z is less than or equal to 1.5? And remember that z, by definition, is a standard normal random variable. Okay, so we have an answer here, 0.933193. I think that looks correct. Let's try it out ourselves. We're looking for less than or equal 1.5. It is a positive value, so we'll go to our positive z values. And I'm looking for 1.5. Now, it's 1.5 flat, right? There's no additional decimal. So really what we're looking for is 1.5 plus 0. And you'll see that for 1.5, my probability is 0.933. So 93.3% probability. So what that means is that at 1.5, about 93% of the entire bell curve will be right there. Okay? So z is my standard normal random variable, and finding these values is simply a matter of tabulating them, not necessarily calculating them, but finding them from tabulated values. We're going to have different types of trials where we go back to these tables. So if you were not able to find it, just try to go through your table, go to the 1.5 column or 1.5 row, and you'll find that the probability is in the first column right next to it. But we're going to get a bit more practice in a second. Now, we've talked a lot about just the math behind finding probabilities for normal distributions. At this point, are there any questions before we move forward? So Carlos asks, so the area under the curve is the probability of z. And Carlos, yes, that is absolutely right. The area under the curve, and let me just rephrase that a little bit, is the probability of z being less than or equal to your value. So in this case, because we were looking for 1.5, if I were to just draw my bell curve, and again, I'm not drawing it professionally or to scale, so it may not be exactly correct, but what we're saying is that at 1.5, the area under the curve, so the area before 1.5, less than or equal to 1.5, corresponds to almost 1, right? To 0.99. I think it was 3. Let me see. Yep, or 933. There we go. 0.933-ish. So yeah, that is the area under the curve. What that means is that if you were to plot this, that you use some nice graphing tools and plot this, and then you calculate the area manually, you're going to get very, very close to this number, because that is the area under the curve. That's correct, Carlos. All right, so now that we understand a little bit about this standard normal distribution, I'd like to talk about why that helps us with other normal distributions, because even though most natural processes are going to follow the normal distribution, not all of them are going to have means of 0 and variances of 1. That's a little bit too precise. However, what we can do is we can relate a normal distribution to this standard normal distribution in order to make our calculations a little bit easier. Now, the process of relating a normal distribution, right, to a standard normal distribution is what we call standardizing. So when I say that we're going to standardize a normal variable, what I'm saying is that we're going to take this normal random variable and we are going to more or less convert it into a standard normal random variable. So let me explain the process a little bit, because it does take a little bit of of thinking to actually do it. But let's say that x is a normal variable. Okay, so x follows a normal distribution with a mean mu and a variance sigma squared. Now, we will find that we can actually create a standard normal random variable, which we're going to call z, right? Because that's a standard normal random variable. We can actually create a random variable by taking x, subtracting the mean from it, and then dividing by the standard deviation. Now, if we do this, and we were to plot this, the distribution would have a mean of 0 and a variance of 1. And that's a really interesting way, a really cool way of standardizing a normal random variable. So for any normal random variable x that has its own mean, its own variance, if I take that x, subtract the mean, and then divide by the standard deviation, the result will be a standard normal random variable, which means that if we were to find the mean of z, we would get 0. And if we were to try to find the variance of z, we would end up getting 1. I'm using these Latin letters for my functions because I don't want to be confused with the mean and the standard deviation or variance of your variable x. So I'll do that to try to avoid confusion. But the idea behind it is that this is how you would standardize a random variable. So a normal random variable, how we turn it into a standard normal random variable. And how does that help us? Because now we can use our z-score tables to actually find our probabilities. So for example, if we want to find the probability that my random variable x is less than or equal to some value, little x, then that should be the same, right? Because probabilities are about proportions of areas. So that should be the same as the probability that my standard normal random variable z is less than or equal to a standard value z. And what that means, applying this, is that what I'm looking for is a probability that, well, we know that z is equal to x minus mu over sigma. So the probability that x minus mu over sigma, where x is just my random variable, is less than or equal to my given value, little x, minus mu over sigma. That's all we're doing. So what we can do now is we can define a value z, little z, and then find our table of z values and find that value, and that should give me the probability that x is less than or equal to little x. So all we have to do is find this little value of z in order to find that probability. And that little value z, you can see, is just taking your target value, subtracting the mean, and dividing by the standard deviation. Of course, we will try it out ourselves to see how that works. Let's go back to our example from the beginning of class, our example where we're looking at current measurements. I think in that example, if I remember correctly, we were looking for current measurements that had a mean of 10 and a variance of 4. And I wanted to find the probability that my measurement was greater than 13. We wrote down the integral we had to solve, but we realized that we can't actually solve that integral analytically, so we're in a little bit of trouble here. But now that we know about standardizing, now that we know how to standardize a normal variable, perhaps we can find a way to determine that probability. So first off, what are we looking at here? This is a normal random variable, so it's a normal distribution with a mean of 10 and a variance of 4. I would like to standardize this and turn it into a standard normal random variable. So let's standardize this this normal distribution? First off, what would my big Z be in this case? We know that's going to be a function of my random variable x, but then how do I take this variable, this x, and convert it into Z? Subtract the mean and divide by 2. Yeah, that sounds good. We subtract 10, right? The mean. And divide by the standard deviation, which is 2. Correct. That is my value Z, right? Now, of course, what I'm looking for is for my little z, right? That my variable is 13. So little z in this case, or little x in this case, will be 13. Okay. So what is my little z value? Well, we're looking for 13 minus 10 over 2. If you're paying attention, you may realize that we're missing something, but we're going to talk about that in a second. How much is 13 minus 10 over 2? Remember, we're subtracting the mean, and then we're dividing by the standard deviation. 1.5, okay. All right. So if z is 1.5, we actually did this example a little bit earlier. Let's find the z value for 1.5, or the probability for our z value 1.5. The probability that z, right, less than or equal to 1.5. We found that in a previous example, it was 0.933193, right? We looked for it in the table. We've already done this. Now, great. My question would be, is that the probability that x is greater than 13? Exactly, right? That's absolutely right. So Sean says that's not the probability, but instead we need 1 minus, right? And where does that 1 minus come from? Well, remember that this probability, all it gives me is the area under the curve before, right, before 1.5. However, what we're looking for is the area under the curve after 1.5. So how do we find those areas? Well, if it's greater than 13, right, the area has to be greater than 1.5 in the z-score table, then all we have to do is we know that the entire sample space will always have a probability of 1. So this area should be 1 minus the area to the left. So in conclusion, my probability is going to be 1 minus 0.933193. And just reading on it, I found a small mistake on the notes. I misplaced a sign here. So I'm going to update the notes again tonight. I uploaded the notes right before the class. So you will have them there so you can see after class, but keep in mind that I have a small sign I need to correct in this example. Okay, so that's pretty much it, right? And I think Sean already gave us the answer. We subtract this is about 0.06681. So about 6.68%. That's my probability. Good. And that's pretty much it. That's pretty much what corresponds to standardizing current measurements, right? We take our normal distribution, our normal random variable, we subtract the mean and divide by the standard deviation, and that is my z-score, my z value. And then I can look for tabulated values and figure out what my probability is. Of course, like I said, even though we have those tabulated values, it's important to understand what this means from a graphical perspective, because graphically, we know that we're not looking for values less than or equal to 13. We're actually looking for values greater than 13. So if we have less than or equal, but we're looking for greater than, all we have to do is take 1 minus our less than or equal values, right? That's pretty much how it works graphically. So that is the normal distribution. This normal distribution is so important that we can even use it, right, to approximate some of our other distributions. So before we take our our daily break today, let's look at some approximations of the normal distribution. So let's find a normal approximation to the binomial distribution. Now, we already remember the binomial distribution, right? We covered it about 2 classes ago, if I remember correctly. The binomial distribution corresponded on running multiple Bernoulli trials, if I remember correctly, right? And the binomial distribution would tell us the probability of landing a success at our first success at certain number of trials, if I remember correctly. This binomial distribution, you'll notice that it can actually be approximated by using a normal distribution. And I'll explain why. First off, when I say normal approximation, what I mean is using a normal distribution to try to approximate another distribution. In the case of a binomial distribution, we could try to define x as a binomial random variable. So a variable that corresponds to a binomial distribution. Now remember that our binomial distributions needed 2 parameters, right? I think our binomial probability mass function required or was a function of parameters n and p, where n is the number of trials, p is the probability of success. Now here's the thing, if we could then figure out what my mean and my variance are for my binomial random variable, we can try to standardize it and then plot it and see what that looks like. So I'll let you browse through your old notes, but for a binomial distribution, what was the mean and what was the variance, if anybody can remind me? Okay, Bailey says that mean is n times p. I think that sounds right. And then Bailey says that variance is np times 1 minus p. So n times the probability of success times the probability of failure. Good. So what we're going to do now is we're going to try to treat this as if it were a normal random variable, which is not, but we're going to treat it as such and then try to standardize it. So we can try to standardize it, right, by defining a standard normal random variable that corresponds to my binomial random variable minus the mean divided by the standard deviation. And if I were to plot this graph, then I would get a standard normal distribution. However, I would also get a standard normal distribution that is going to be very, very close to my values for my binomial random variable. I'm not going to try to graph it myself because I'm not going to be able to draw it nicely, but I'll show you from a picture from the book to see what that approximation looks like. So this is what the approximation would look like. These little points here represent the values of the binomial distribution. Remember, binomial distribution is a discrete distribution, which means that you have specific values for specific probabilities for specific values. However, if I can plot my standard normal approximation here, you'll see that the standard normal approximation actually goes through most of the points in my binomial distribution, right, with the exception of the mean or the middle point. And you'll notice, right, this is for n of 10, so for 10 trials. You'll notice that the more trials we add, then the closer this approximation becomes. So we can use our normal approximation, right? We can try to standardize a binomial distribution, which isn't even normal. And you'll see that our approximation is going to be very, very, very close to the actual distribution itself. Now you may be wondering, well, why does that happen? Well, recall that we said, right, and this is part of the general definition of a normal distribution. We said that most physical processes, most experiments, when you repeat them multiple times, they tend to approach a normal distribution. And that's exactly what we're seeing here. So think of it conceptually, like what does a binomial distribution mean, right? A binomial distribution is simply repeating an experiment multiple times where the experiment has one of two outcomes, and those outcome probabilities are independent of each other. So something like flipping a coin. But we can see right now, right, that binomial distribution, if you increase the number of experiments, it actually tends to look like a normal variable, a normal distribution. In fact, it tends to look like one so much that we can actually approximate it as a standard normal random variable. Now, you may be wondering how this would work in the case of, for example, flipping coins. Because flipping coins, you only have two outcomes. How can there be a middle point? How can there be extremes? But remember, the binomial distribution is not about the individual experiments. It's not about the individual trials. It's about all the trials as a whole. So you think about it, your binomial random variable isn't just heads or tails if you're flipping a coin. It's what outcome you had, right, across your entire experimental run. Okay, and you'll see, right, you can see that even those values follow a normal distribution. Once you plot them, you notice that they actually seem to look more and more like a normal distribution. We'll find that throughout the entire class, a lot of different phenomena that we're going to be studying, they're going to tend to look like a normal distribution. They're going to tend to follow the central limit theorem. Now, of course, you'll notice that the points aren't exactly all there, right? Some of the points, specifically the mean, is not at the correct value. So the approximation isn't perfect, but it is pretty useful. Now, some empirical analysis has been able to determine how to correct our approximation just to make it a little bit more precise. This is what we call a continuity correction. A continuity correction is when we try to apply a correction to our approximation to make it a little bit more precise. And what my continuity correction will be, we'll say, is that the probability that x is less than or equal to x, that's for our binomial distribution, is going to be almost equal to the probability that my standard normal random variable z is less than, and here for my little value, I'm going to have, instead of just x minus np, I'm actually going to have x plus about 0.5. So adding that 0.5 allows us to correct our data slightly so that my approximation becomes a little bit more exact. Likewise, if we want to find the other way, if we want to find the probability that x is greater than or equal to little x, we can approximate it by taking the probability of our standard normal variable. And here, our x will subtract 0.5 from it. The subtraction allows our approximation to be just a little bit more precise. And there isn't really an analytical or mathematical way where we just derived and got that 0.5. Instead, this is an empirical correction, where after looking at different data sets and running multiple experiments, statisticians found that adding 0.5 or subtracting 0.5 allows you to make your approximation very, very precise. Now, of course, this is an approximation. And if you recall the photo we saw from the textbook, and let me just pull it up here again. If you recall this picture, which is also in your textbook, you'll notice that the more trials, then the closer your approximation will be. But of course, you realize that if you reduce your trials to, let's say, 2, for example, it'll be very, very hard to actually fit a normal distribution into it, right? It's going to be very hard to approximate it by a normal distribution. So of course, there have to be some limits, right? There have to be some limits to how we use this approximation. Now, the approximation with this specific continuity correction of 0.5 is valid for a range, and that range will be for a mean greater than 5 and for n1 minus p greater than 5. So n times probability of success greater than 5 and n times probability of failure also greater than 5. So if these two parameters are met, then this approximation should work, should approximate my values with relative correctness. We don't just use the normal approximation for binomial distribution. We can also use our normal approximation to approximate the Poisson distribution. Now, while I start writing this down, why don't you look through your notes so you can let me know what the mean and what the variance or standard deviation was for the Poisson distribution. All right, thank you, Renee, in the chat for finding the mean and the variance for the Poisson distribution. Now, for Poisson distribution, my mean and variance are actually functions of my interval, right? We have lambda, which is the average value across the interval, but we also had the length of my interval. So for our approximation, we're going to be a little bit different. We're going to not use the interval or assume that the interval is just 1, right? Because one way to standardize this is going to relate to making our values as simple as possible. So in this case, if we let our interval length be equal to 1, right, our intervals be equal to 1, then we could standardize my Poisson variable by taking x minus lambda, we let t equal 1, then divide by the corresponding standard deviation, which if the variance is lambda t, but we're taking t as 1, then the standard deviation would just be square root of lambda. Doing so allows us to approximate our Poisson distribution. Now, this approximation is valid only for lambda about greater than 5. Small numbers will not really work. Now, we can actually solve binomial and Poisson distributions by applying our normal approximation. All we have to do is create our random variable, c, our standard normal random variable, and then we can find the corresponding z value from our tables. We can then compare to our calculated values, and you'll see that as long as your conditions are met, lambda greater than 5 for Poisson, then your approximation should give you very, very close values. We're not really going to go over examples of this in class because the focus of this class will not be normal approximations. It's actually just using the normal distribution in general. But if you do want some additional practice, you can look at examples 4.13, 4.14, 4.15, and 4.16 of your textbook. Those examples will allow you to have a good idea of how these normal approximations work and how they compare to their actual calculated values. We're about halfway through the class, so let's take a 15-minute break and we'll meet back at 3:30.